Alright guys, for this lesson, basically what we want to do, we want to start off with just talking about some of the things that we've discussed so far in class over the first few days. So starting off, we talked about linear equations, and in particular, how can we represent lines? So we talked about standard form, point slope form, and slope intercept form. Alright, so just representing lines, how do we write the equations of lines and so on. Next thing we talked about, sticking with basic equations, we talked about perpendicular and parallel and what that means to us algebraically. And generally we just talked about slope, and I think you guys understand that, so I don't want to dive into that any further on here. The next thing we talked about were absolute value functions and equations and inequalities. Solving those, graphing those, and so on. Alright, so that just kind of gives you an overview of where we've been. What we want to get into now are systems of equations. So we've talked about some of the basic equations and some of those characteristics, and we want to get into systems of equations. And so in order to do that, in order to introduce this concept, what we want to do is we want to look at this little applet right here. This applet allows me to fire a cannon. We can change the angle on that cannon. But essentially, I'll just fire this a couple times. And you can see up here it's going to measure a couple different things. It's going to measure range, it's going to measure height, it's going to measure time up here. And there are a lot of other things that are measured, but I want you to focus on this up here. Alright, so we fire this cannon. Our goal essentially is to hit this target. I'm going to put it, let's go right there. Let's see how I do here. You fire your cannon, comes down, and miss. There's a miss. So here, what it's going to do is it's going to map the path, which hopefully we're all familiar with what sort of function this is going to be. This is going to be a quadratic function. But notice what it takes note of up here. It takes note of the range. The range is 21 meters. The height, and this is the ending height, is negative 1.2. So it's 1.2 meters below where it started. And then the time that it took from when it fired and landed over here was 3.5 seconds. Let's adjust this a little bit, try to hit our target. So we're going to move it up a little bit, make that path a little bit more shallow. And I just want you to pay attention up here at what's being measured and how those things change as it goes. So there's my tank shell, there's my cannon, and there's a score. And again, you can see as it changes, it's going to measure how far it goes in the horizontal direction, how far it goes in the vertical direction over time. All right. So the concept that we want to look at is we want to look at how can we actually map these? How can we actually come up with equations that map the path of this thing? And if you go back, we said this is strictly a function of time, and this is strictly a function of time. So the way that we write these equations, we'd actually have to map two separate equations. Our first equation, they called range. We're just going to call really distance in the x direction. We know that the distance in that x direction is a function of time, so our function might look something like this. X of t equals, and then whatever function or equation is going to actually map the path of that thing. It's going to be different depending on how we angle that cannon. So for range, we have one function. For height, we have a completely different function. It's still dependent on time, but that height, y of t, is completely dependent upon how much time has elapsed. And while this is actually going to be linear, this function right here, and the parent function or the standard function is, it should be t squared. the parent function for this particular thing is going to be t squared, and obviously it'll change. This is a quadratic. So what we want to look at here is what happens if I don't want this to be dependent upon time anymore. I want to write a function that essentially predicts height, or gives me the height of that cannon shell based on how far it's traveled in the x direction. Or distance in the x direction. So just notice what we're doing. Essentially, we want to create a function that predicts height. So that would be our y. We want to predict height based on how far, or based on the distance traveled in the x direction. So what we want to do is we want to come up with a function that's no longer dependent upon time, like these functions are, but it's now a height function dependent upon how far you've traveled in the x direction. Or if you want to flip that, we can create a function that predicts the distance traveled based on how high that thing is, and that would be a function that is essentially x of y. Our distance is dependent upon the height traveled. All right, so we call these parametric functions. These are parametric functions where our parameter is t. And down here, we no longer have a parameter. What we're doing is called eliminating the parameter. So we want to get rid of this parameter that kind of tells us separately what these two things are doing. And we want to combine them into one function so that I can predict one value based on the other, or vice versa. So we're going to be looking at these parametric equations and parametric functions. First thing we want to do is we want to talk about domain and range, specifically for an example like this. So I've got these two this parametric system right here. X is dependent upon time, and here's just a linear function. Y is dependent upon time. Here's another linear function. And we want to look at where t is greater than or equal to 0. A lot of times, anytime you talk about parametric equations where time is the parameter, you're going to look at a scenario where time is greater than or equal to 0. You're going to start measuring whatever these two values are. You're going to start measuring at a time of 0, moving forward in the positive direction. So what we want to do is think about the domain and range of these two equations individually based on the parameter time. All right, well, hopefully domain is a relatively easy answer here, an easy concept. So my domain on this particular function here, I can only plug in, my input values are going to be times, and I'm going to start at 0. So because this is linear, I'm going to plug in a value of 0. That's the lowest value I can plug in. And we're going to go up from there. So if I'm going to write this in set notation, I've got all of the t values in the real numbers. So all real number t's, such that t is greater than or equal to 0. And it's actually the same thing over here. I've got a domain over here from y of t, where my t values, again, I'm going to plug in the same values here. Those are real numbers, and those t's have to be greater than or equal to 0. All right, my range values. Now let's think about what the range values are going to be on this thing. If I plug in 0 for t, which is the least domain, or the lowest value for the domain that I can plug in, my x of t is going to spit out something that looks like this. My outputs are now x's, so we're going to have all of the x's in the real numbers, such that what's going to happen? Well, the lowest value I can get is 3, so my x's have to be greater than or equal to 3. And I'm going to get all the rest of those values based on plugging in domain values from t. All right, a little bit different here. but similar process. We're going to take all of the y values, all real number y's. So y is in the real numbers such that, and think about what's going to happen. We plug in 0 for t. 5 minus 0 is going to give me 5. That's actually going to be the greatest value that I get. If I plug in 5 minus 0, I get 5. So when t, and if you're struggling with this, guys, make a chart, okay? Make a chart. This would be my suggestion for all of you. For linear functions, it's not crazy difficult, but it can get a little bit confusing, especially in the beginning. So all we're doing is plugging in the least value for t, so 0, 1, 2, and hopefully that'll establish a pattern for us. For our x's, go back to the x's, plug in 0 and you get 3, plug in 1 and you get 4, plug in 2 and you get 5, and everything's going to be greater. So we can establish a pattern there. Plug in 0 for y of t, and we're going to get 5. Plug in 1 for y of t, you're going to get 4 and 3, and so on. So to finish up our range values here, our range values are going to be real numbers such that y is always going to be less than or equal to 5. You're never going to get anything greater than 5. Alright, so from here, first question, is this a function? Well, hopefully we all recognize, yeah, this is a linear function. So that one checks out, it's linear. Same thing over here. This is a function. This is a linear function in particular. Next thing we want to look at is, where is the starting point? So where does this thing start? Well, my first starting point is going to be at a time of 0. And the output, or if we're talking about horizontal distance here, the horizontal distance is going to be 3. So at a time of 0, remember this is t, that's my input, and my output is x. So my starting point here is going to be 0, 3. The next point, if we wanted to list the next point, well, I guess it doesn't have to be whole numbers, but we can list another point at a time of 1. We would have an output of 4, or a horizontal distance of 4. All right, same type of deal over here. Starting point over here for y of t, that function. Remember, our inputs are time, and based on time, we're going to determine how tall this thing is, or what the height of this particular object is, based on this equation up here. So again, initial point or starting point at a time of 0, we're going to have an initial height of 5. So there's my starting point for each one of those. Alright, so if we want to go back to our little example up here, I want to keep it as simple as possible. So what we want to do in order to map this is just to kind of say, hey, what happens if, to generally give our example some legs here, we know that y of t is going to be equal to some kind of quadratic. And I want to use the simplest quadratic because we're just kind of getting started with this stuff. So here's the height of this particular cannon shell as a function of time. And we know it's a parabola, so it's going to be mapped by a quadratic. If I want to make this as simple as possible, what I need to do is I need to go in here and I need to say, hey, my horizontal distance as a function of time, let's just set that equal to t to make it the most basic linear function. All right, well, if I go back over here, in order to do that, I need to make sure that this thing is traveling 3.6 seconds. It's traveling 3.6 seconds, so I need to make sure that over 3.6 seconds, it only travels 3.6 feet. So we need to raise this up pretty high here. Let's see if we can even do that. Not bad there, 3.7 seconds there, 2.8 meters traveled. So let's flatten it out just a bit. Hopefully this will get us close and you guys can kind of get an idea. Well, we're not on. But hopefully you guys get the idea. Somewhere in between these two functions, that horizontal distance traveled is going to be the same as the time that has elapsed. And so we'll have two parametric, or a parametric system that looks like this. And again, the parameter, this is going to be restricted by the amount of time, and our amount of time is always going to be greater than or equal to 0. So just to give you some closure, try to give you some closure on this whole idea. Basically, using our example, I want to eliminate this parameter t. I want to get rid of it. In order to get rid of it, I want to write a function of height as determined by the distance traveled horizontally. All right, so this function y of x would be my height as a function of horizontal distance. And now we've eliminated time as a factor here, or more specifically as a parameter for these two functions. All right, so we can directly relate height to horizontal distance traveled, as opposed to having to have this this parameter time that kind of governs what's going on with each individually.